What if your next receptionist could navigate crowds, ride elevators, and interact all on its own? Meet Mobile Robot Receptionist 2.0, a smart solution for dynamic navigation and human-robot interaction. Our current implementation builds on earlier stages developed since 2018, starting with a stationary robot and evolving to autonomous indoor navigation in 2023. Now, we're expanding its capabilities to include multi-floor navigation, crowd interaction, and advanced human-robot engagement. We began by identifying key challenges in current robotic receptionist systems: limited navigation in crowded spaces due to occlusions and dynamic obstacle detection, restricted mobility across floors from limited elevator interaction, weak human interaction capabilities, especially gesture recognition and social compliance, and finally, an inability to utilize surrounding resources like elevators for complete building access. Our project is built around 4 key objectives: enabling autonomous navigation across multiple floors, ensuring safe and efficient crowd navigation, achieving robust interaction with conventional elevators, and incorporating intelligent self-charging capabilities for long-term deployment. To test our concepts, we developed a simulation environment in Gazebo from the ground up. This environment replicates elevator behavior using both position and velocity controllers. We integrated the SLAM toolbox and ROS2 navigation stack with behavior trees to orchestrate multi-floor navigation routines, including elevator detection, boarding, and goal completion. In real-world use, users set floor-level goals via a GUI. The robot autonomously navigates to the elevator, detects the button panel using RGBD input, and identifies buttons with a trained YOLO model. It completes the interaction in under 4 seconds, handles conventional elevators, presses the correct button inside, and resumes navigation upon reaching the target floor. To enable effective interaction with elevator buttons, we upgraded our robotic arm from a 3 degree of freedom to a 4 degree of freedom design by adding a joint between the shoulder and elbow. This provided greater flexibility and range of motion. Prior to design, we performed torque calculations to select suitable servo motors, and the arm was modeled and assembled in SolidWorks. A URDF file was then created to integrate the design with ROS2. We implemented a fully autonomous framework for elevator interaction. The robot approaches the elevator, detects the button using a pre-trained YOLO model, and calculates its 3D coordinates with depth data from a RealSense camera. These coordinates are transformed into the robot's base frame, and MoveIt handles inverse kinematics and trajectory planning. An endoscopic camera and a ROS2 node were used for precise fingertip alignment before pressing the button. The robotic arm replicated gestures like Ayubawan, show left, and show right more realistically with the improved joint configuration. The robot uses a self-charging system to dock and recharge without human help. It navigates to the docking station using the ROS navigation stack, and an ultrasonic beacon guides precise alignment. Once docked, the robot activates the charger, connects to the power supply, and begins charging. A voltage sensor and BMS handle battery monitoring and safety, allowing continuous autonomous operation. The power system includes 3 parts: the dock station with a power supply, converters, and relays, onboard charging modules with BMS and power converters, and custom PCBs with relays and sensors for controlled docking. Together, they ensure safe, efficient, and fully automated power management for the robot. Crowd navigation helps robots move safely through moving groups of people. We built and tested our system using the CrowdSim 2D simulator. Orca predicted human movement, while model predictive control guided the robot, enabling smart, real-time decisions to avoid collisions. To move closer to real-world deployment, we tested our system in a 3D gazebo simulation. HuManNav Sim added realistic human behavior, while YOLO V10 and LiDAR powered accurate detection and tracking. This setup enabled smooth, collision-free navigation, bringing us one step closer to real-world crowd interaction. After extensive simulation and testing, we transitioned to real-world experiments. Here, our robot navigates around actual human agents in controlled indoor settings, from single individuals to dynamic multi-agent scenarios, demonstrating safe, intelligent motion in live environments.